All right, we've got one more force to study, the rather common yet mysterious force of gravity. Right? If we believe Newton's laws of motion, which are tested, we don't have to. We might say, no, that's not right. Aristotle had ideas about it, but those didn't turn out to work out very powerfully. So if we believe Newton's laws of motion, and I let go, this will accelerate. It hits a certain speed there. It hits traveling faster. So the farther it falls, the faster it goes. Just try it out, with a bowling ball or something. Drops farther, it's going to go faster. So it's accelerating, and yet nothing's touching it. Now it is. It's in equilibrium, static equilibrium. I let go, it accelerates. We know this. Acceleration is down, 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 down. The entire time, acceleration is down. At the top, the acceleration is down. Something is causing it to accelerate. So we blame it on something. Right? We've always got to blame our forces on something, which is going to come up when we do circular motion here in a bit. You've got to blame it. There's got to be a source for the force, and it's got to be an object. Gravity is not the source. It is a type of force. Let's explore those equations a little bit now. And of course, the punchline will be kind of easy, but it's tricky. We're so used to gravity that we just kind of take it for granted, right? But not us. Okay, so what is the force from? I don't know. Mass. Mass plays two roles: inertia and property responsible for gravity. If you want to do warped space-time with general relativity, well, you got to work through these courses first to get there. So mass, somehow, right? The type of force is gravity. And think about an object orbiting, Earth orbiting Sun. Is it accelerating? Moon orbiting Earth. Is it accelerating? It's turning, let alone the fact that the speed is changing little by little. So it's turning, it's accelerating. You got to blame it on something. So you blame it on something. Newton developed the force of gravity called the universal force of gravity. We're going to see that here in a second. If you asked him, but why? How does Sun pull on Earth? How does Earth pull on Moon? Then he'd probably say, shut up. I don't know. But clearly it's accelerating, so I got to blame someone. We blame it on this force we call gravity. It is only an attraction. Now, you might say, look, my hand is balancing gravity. So is my hand anti-gravity? Well, that's not what we mean. Anti-gravity would be some other force that is opposite to gravity, or some repulsion from gravity or something. So we don't know of that. For some reason, it's an attraction. All right, we'll go with that. So it's an attraction. So draw your picture, look at it. What's your receiver? What's your source? Put it in. You're good. All right, let's go over here. Force of gravity. How strong is it? Well, there's two main ways that we're going to look at this. I'm just going to mention this. You're not going to get into this more than likely, but you might in upper division if you were to do this. The most general case is you've got to add up or integrate mathematically the force of gravity from every piece of your source object on every piece of your receiver object. Have fun. It is kind of fun, right? So if I look at this, if the red pin is my source and the green one's my receiver, then every piece, like the cap, pulls on every piece of the green pin. And then the next little bit pulls on every piece of the green pin. And the next little bit, and so objects of this shape, we have to use integration and break them down. But if they get farther and farther away, they start looking smaller and smaller, and you can imagine them to be spheres or point objects. And common saying is for physicists, we always say, imagine a spherical cow. So we can do that. Realize that the force of gravity between these two is kind of complicated unless we treat them as smaller. Those aren't really spherical, but they're getting closer. And we move them down or move them away where the shape becomes insignificant compared to the separation. So what if we do have the special case of spherically symmetric mass distributions, where there isn't more mass over here, but it's spherically symmetric, or point-sized objects, or just approximation, a good enough equation for us. Then we've got our source object and our receiver object. You could flip it, just be clear what you're looking at. And we got the force of gravity from S on R is, this is Newton's law of universal gravitation. Some gravitational constant G, the mass of the source, this guy, the mass of the receiver, that one, the separation between the centers, remembering that they're spherical or point size, and so from here to here would be this separation, R from the source to the receiver, squared. And that'll be, of course, in newtons or pounds or whatever force units you've got. This, of course, is in kilograms. This is in kilograms or grams. Let's work in the SI or MKS system. So let's check that guy out for a second. What would the units of G be? You should be getting good at this. Just pop out. This is newtons. So solve for G and put in the units. This is going to be newtons, right? I'm going to divide by a kilogram and a kilogram. That goes here. This goes up top. So I'm going to multiply times a meter squared. And those are going to be the units of, make an arrow because it's not equality, the units of G. How strong is G? That's a tricky thing to measure, and it's gone through some steps, but G is, look it up. I'm going to leave that, 6.67, times 10 to the negative 11, what units? Oh, I just think in my head, Newton divided by kilogram squared, meter squared. What you should realize is that it's tiny. And so while I am pulling on this pen, when I let it go, it isn't going to stick to me. That'd be a cool little trick. But, you know, guess who wins? Earth, obviously, because Earth has got enough mass to overcome the fact that this is tiny. I don't have much mass compared to Earth. And so my force on the pen is not going to be very significant. In fact, it's kind of fun to look at that and realize that the force from people around you of gravity is stronger on you than the force from stars or planets, and so they likely aren't going to affect your personality. Anyway, this is universal force of gravity. This is fine, and that's just an introduction to that, and that's how you would deal with it. That's the distance between two spherically symmetric objects. Let's keep going now. What we're going to do now is, for most of our problems, we won't use that. We'll use something else. So we're going to look over here near the surface of Earth, where we do our experiments. And near the surface of Earth, you've got a little object here, really much smaller than that. Our atmosphere is thinner than that line. Here's Earth, which is not exactly a uniform distribution of mass. You've got different things, different places. But we'll take this to be the distance between the center of our source, namely Earth, and our object, I'll call it R. There's our object. It has a certain mass, m of r. This has the mass. I often like to do a capital M for big masses, mass of Earth. That's fine, or lowercase. So check this out. This one's fun. Try it. Do it. We take G, and look up that universal gravitation constant, times the mass of the source, divided by the distance between the source and the receiver. The source is Earth. Look up that number. Multiply it times that number. You got to do this. It's so cool. Take the radius of Earth, which is pretty much the separation. I mean, from here to the ground is not the distance. It's from here to the center of the Earth. And here to the center of the Earth is not much different than here to the center of the Earth and here to the center of Earth. So what you get is a constant, a constant, a constant. And guess what number you get? 9.8 meters per second squared. Check the units, get everything, do that, and you go, cool, that's G. Is that gravity? No. Is that the force of gravity? No. Is that the acceleration? Not necessarily. I still have the force. Only when I let it go is that the acceleration. So what I've got is that the force of gravity from Earth on some receiver near the surface is equal to the strength. We know the direction is down, call that plus or minus, doesn't matter, but is equal to G, mass of Earth, mass of the receiver, distance between, the center of Earth and the receiver. That's G, mass of the receiver. And so we finally get the equation that you've probably seen, but now hopefully you know it a little better. The force of gravity, for all intents and purposes on our objects in the lab and everything, is going to be the mass of the receiver times G. Notice the units. The mass is, for example, kilograms. So that would be kilogram meter per second squared. And of course, that is a Newton. Okay? That's the strength of the force downward, the force of gravity from Earth whenever you're near the surface. And so if you have to worry about it, it is varying. It's weaker here than it is here, and a little stronger here, but not so much that it's going to make a difference. Even in orbit, in a close orbit, you can check that out. Just add on to the radius of the Earth 300 miles, convert it, it's fun, and you'll see that, wow, it's not that far off. Okay? So that is the force of gravity. Now that doesn't tell you the acceleration. This is not free flight acceleration. Let's take a look. Not acceleration. Okay? It is, G is the free flight acceleration, so it's only acceleration when it's in free flight, right? Not now. Now. Okay, so let's take a look at that. Right, so that's going to be our equation, nice and easy. Force of gravity is mg, unless we move on to the universal force of gravity. But it comes there, it's nice, and it can predict things like the orbits of the planets fairly well. So let's take a look over here. Remember our force analysis steps. Decide to do force analysis. You don't always. You might do kinematics, energy, momentum. Choose your object, your receiver, R. Do a free body diagram, which means put in the forces. Here's R. I'm going to do the case of free flight, or free fall, as it's usually called, but it can be going in. Okay, so I'm throwing it. Air resistance is negligible, no rockets, nothing else. I'm not holding on to it. So what are the forces on that thing? There's only one force. It's the force of gravity. Okay, great. Force of gravity. Now, that looks good. I need to choose my coordinate. I'm done, right? That's all I've got. I need to choose and label my coordinates. I'm going to call, it doesn't matter, I'm going to call up positive y. And I'll call this positive x. The acceleration x is 0. The acceleration y is negative g in this case. Okay, fine. Components, table. We're going to do, we're getting near the end. Components table. We don't need to do it. We just got this right here. So we don't need Newton's second law in each direction. Well, the sum of the force x equals max. The sum of the force y equals may. There's no forces in the x direction, and there's no acceleration, so nothing's really happening much when it comes to Newton's second law in the x direction. In the y direction, we have the force of gravity down, so it's minus this, and in this case, we've got the mass of the receiver times the acceleration, which is negative g. And so here we have, once again, found the force of gravity to be, getting rid of those negatives, force of gravity strength is equal to the mass of that object times g. In this case, g is the acceleration and mg is the force. But we're going to see next cases where that's not true. So be careful. Don't use g as the acceleration. mg is the force. G is the acceleration only in free flight. Are we? Oh, good. So, another point here. Look at that. It's in free flight. Which way is it going? Which way is that object going? I said it's free flight, so that means no forces but gravity. Gravity is attractive, down. The only thing that is significant is from Earth. But could it be going up? Sure. Then it would be decreasing speed. Could it be going down? Sure, it'd be increasing speed. Could it be at the top? Sure. And then it would be changing. It would slow down and stop for a moment, not stop and stay, and increase speed. Decrease speed, stop, increase speed. Right? So changing all the while. Could it be going sideways? Yes. Could it be going down and sideways? Yes. So again, force analysis does not tell you about velocity directly. You can get there relating acceleration to velocity through kinematics, whatever means you have. But acceleration doesn't directly tell you about velocity. You can have a high acceleration, low velocity, and vice versa. You can have no acceleration, and you can have velocity. You can have no velocity, and you can have acceleration, right? Because the next moment, you won't have no velocity. So be really careful. Free body diagram is this. The force of gravity is mg, and in this case, the acceleration is g. That's it. That's the only time we're going to get acceleration of g, unless you're somehow strangely lucky. Don't do a component table if you don't need to. In this case, that would be overkill. But if you have a few forces in there, certainly do that. So I think we're gonna move on to the next set of examples in the next video, and we're going to answer the question: why is it that when Galileo dropped two objects from the Leaning Tower of Pisa in his mind or in actuality, well, what happened and why? Seeing this will require you to see math playing two different roles, again, as we've laid that foundation. And you really will understand it. Most people don't. It's tricky. Unless you pause and think about it, you won't get it right. If we do the force analysis carefully enough, you'll see it all makes sense. So let's do this again next time with some examples.